All right, so in calculus, you've probably learned all about the fundamental theorem. It's an amazing tool, right? But what happens when it just doesn't work? What if you run into an integral where finding that antiderivative is, well, pretty much impossible? That's what we're tackling today. We're going to crack the code on numerical integration, a set of super powerful techniques that let us find the area under a curve when our usual methods just won't cut it. So here's the game plan. First, we'll look at these impossible integrals to see why we even need to approximate. Then, we'll get into our toolkit of shapes, covering the trapezoid rule and the real star of the show, Simpson's rule. We'll put them to the test with an example, and finally, we'll figure out how we can be absolutely sure our answer is accurate enough. All right, section 1, the impossible integral, or why sometimes the best answer is just a really, really great guess. So what's the deal? Why can't we just use the fundamental theorem for everything? Well, the truth is, a surprising number of functions out there are stubborn. They don't have what we call an elementary antiderivative. That's just a fancy way of saying you can't write down their integral using the usual suspects, like polynomials, trig functions, or logs.
And that brings us to the big question, right? What do you do if an integral is impossible to solve with the fundamental theorem? I mean, if you can't find that antiderivative, how on earth are you supposed to find the area under the curve? If a perfect exact answer is off the table, what's our plan B? And trust me, this isn't just some weird abstract math problem. We're talking about some famous, heavy-hitting integrals here. You've got the Gaussian integral, that's the bell curve from statistics, a huge deal. Then there's the sine integral, elliptic integrals. These pop up all over the place in physics and engineering. And for every single one of them, there's just no simple formula you can write down for the answer. So, what's the workaround? Well, it's actually kind of beautiful in its simplicity. The idea is this. If we can't figure out the exact area of that weird curvy shape all at once, let's just chop it up. We can slice it into a bunch of simple shapes that we definitely know how to measure, like rectangles or trapezoids. Then we just add up the areas of all those little pieces. It's a brilliant way to get an answer that's darn close to the real thing. Okay, section 2, approximating with shapes. Think of this as your calculus toolkit. We're going to look at a few different methods, and you can really think of them as good, better, and best when it comes to accuracy. So the first tool in our kit is the midpoint rule. It's pretty straightforward. We're using rectangles to estimate the area. But here's the trick. Instead of taking the height from the left or right side, we measure the height right from the center of each little interval. And what's cool about this is that it's often way more accurate than you think, because the little bit you overestimate on one side tends to cancel out the bit you underestimate on the other. It's a clever little balancing act. Next up, we have the trapezoid rule. This is our better method. Instead of flat tops like rectangles, we connect the dots. We take the function's value at the start and end of each interval and draw a straight slopes line between them. This creates a trapezoid. And as you can imagine, that slanted top usually hugs the actual curve a lot more closely. And now for the best, the powerhouse of approximation. Simpson's rule. Okay, this one is seriously cool. Instead of using flat lines or even slanted straight lines, Simpson's rule uses parabolas. It takes 3 points at a time and fits a little piece of a parabola through them. Since parabolas can actually curve, they can mimic the shape of the function with incredible accuracy. Now, there's one important catch. For Simpson's rule to work, you absolutely must have an even number of subintervals. Okay, let's put it all together. This table gives you a really nice side-by-side look at our three methods. You can see the different coefficient patterns, especially for the trapezoid and Simpson's rules, and the takeaway is pretty clear, right? As we go from rectangles to trapezoids to parabolas, the accuracy just gets better and better. All right, section 3, the trapezoid rule in action. Enough theory, let's actually put this stuff into practice. We're going to start with an integral we actually can solve, so we can check our work and see how good our approximation really is. So here's our mission. We're going to approximate the integral of x squared from 0 to 4. We're looking for the area under that classic parabola. And to do it, we'll use the trapezoid rule with exactly 4 subintervals. Okay, so how do we do it? It's a 3-step process. First, we need the width of our trapezoids, delta x. That's just 1 in this case. Simple enough. Step 2, we plug in our x values, 0, 1, 2, 3, and 4, into our function to get the heights. That gives us 0, 1, 4, 9, and 16. And finally, step 3, we plug everything into the trapezoid formula. Don't forget the most important part, you gotta multiply all those interior heights by 2. And when you crunch the numbers, you get an approximate area of 22. Now, the actual exact answer is 21 1/3. So we're really close. Our error is less than 1. Honestly, not bad at all for just chopping it up into 4 simple trapezoids. Section 4, Simpson's rule, the best bet. So 22 was a pretty good guess, but can we do even better? You bet we can. Let's try the exact same problem, but this time we'll unleash the power of Simpson's rule. The nice thing is, all the initial work is already done. Our delta x is still 1, and our function values are still 0, 1, 4, 9, and 16. The only thing that changes is the formula. Instead of that 1, 2, 2, 1 pattern, we use Simpson's unique 1, 4, 2, 4, 1 pattern. That's the secret sauce. And when we plug those values into Simpson's formula, we get 21.33 repeating, or, if you prefer, exactly 64/3. Wait a minute, that's not an approximation. That is the exact answer. How is that possible? Why did Simpson's rule totally nail it? And here it is. This is the big aha moment. Here's a fun fact for you. Simpson's rule isn't just a good approximation for polynomials. It's perfectly exact for any polynomial up to degree 3. Since our function, x squared, is just a simple degree 2 polynomial, the parabolas that Simpson's rule uses to approximate it, well, they weren't approximations at all. They were a perfect match. Okay, section 5, guaranteeing your accuracy. This brings us to a really practical question. How good is good enough? I mean, in the real world, you might need your answer to be accurate within, say, 1/1000th. So how can you figure out how many intervals you need to slice your function into to guarantee you hit that target?
The tool for this job is called the error-bound formula. Now, what's really important to understand is that this formula doesn't tell you exactly what your error will be. Instead, it gives you a guarantee. It calculates a worst-case scenario, a ceiling for your error. It tells you, no matter what, your actual error is guaranteed to be less than this number.
So how do you use it? It's basically a two-step dance. First, you have to find this value k. K is the maximum value that the second derivative of your function hits on your interval. And the second derivative is really just a measure of how curvy the function is. So k is like finding the peak curviness of your graph. Once you've pinned down k, you just set up the error formula, tell it how much error you're willing to tolerate, and solve for n.
Let's make this real with one final example. Imagine we need to approximate the integral of 1 over x from x equals 1 to 2. And here's the catch. We have to guarantee that our answer is accurate to within 0.001. How many trapezoids are we going to need? Well, for this particular function on this interval, it turns out that the max curviness, our k value, is 2. So we plug k equals 2 into our error-bound formula, set the error to be less than 0.001, and we solve for n. What we find is that n squared has to be bigger than about 166.7. Take the square root, and you get n needs to be 13 or more. So there you have it. If we use at least 13 trapezoids, we can be confident our approximation is definitely within that tolerance.
So at the end of the day, the fundamental theorem of calculus is amazing, but it's not the only tool in the box. When it can't get the job done, numerical integration steps in. It gives us this incredible toolkit to find the area under pretty much any curve. And with methods like the trapezoid and Simpson's rule, plus the power to guarantee our accuracy, we're ready to take on all sorts of complex problems. So now you have the tools. The only question left is, which impossible problems will you choose to solve?